Okay, let me just quick make sure that I'm actually online. Alright, Stream Manager. Hopefully we don't have bad internet problems today. We should be good. Alright, is stream up and running? Let's check. Alright, Twitch, if you could load slightly faster. Reminder that I'm streaming all these readings on twitch.tv/xdd4less3. Okay, it looks like we should be good to go. So, no more delaying, let's just get on with it. Chapter 11, Homomorphisms. One of the basic ideas of algebra is the concept of a homomorphism, a natural generalization of an isomorphism. If we relax the requirement that an isomorphism of groups be bijective, we have a homomorphisms. Section 11.1. Group homomorphisms. A homomorphisms between groups G dot and H circle is a map phi from G to H, such that phi of G1 times G2 equals phi of G1 composed with phi of G2 for G1 and G2 and G. So we have a map phi from G dot to H circle such that phi of G1 times G2 is equal to phi of G1 composed with phi of G2. So in a sense, we have a map that respects the group operation. However, note that it respects the group operation and nothing more. So not required to be 1-to-1 to 1 or onto. The range of phi in H is called the homomorphic image of phi. Two groups are related in the strongest possible way if they are isomorphic. However, a weaker relationship may exist between the two groups. For example, the symmetry group S sub n and the group Z sub 2 are related by the fact that S sub n can be divided into even and odd permutations that exhibit a group-like structure as in Z2, as shown in the following multiplication table. So we use homomorphisms to study relations such as the one we have just described. So for example, in this case, we can have a homomorphism which sends like odd permutations to 1 and even permutations to 0, Z mod 2. Example 11.1. Let G be a group and G be an element of G. Define a map phi from Z to G by phi of n is equal to G to the n. Then phi is a group homomorphism, since phi of m plus n equals G to the m plus n equals G to the m, G to the n equals phi of m, phi of n. This homomorphism maps Z onto the cyclic subgroup of G generated by G. Note as well that it's very possible that the element G has finite order, but we're still able to define this. Even though the group has finite order, we're not requiring that this homomorphism be injective. Example 11.2. Let G equal the general linear group of 2x2 matrices over the real numbers. If A is equal to ABCD is in G, then the determinant is non-zero. That is, the determinant of A is equal to AD minus BC is not equal to 0. Also, for any two elements A and B in G, determinant of A times B equals the determinant of A times the determinant of B. Using the determinant, we can define a homomorphism phi from the general linear group with 2x2 matrices with real entries to the real numbers under the group action of multiplication by A maps to the determinant of A. Example 11.3. Recall that the circle group T consists of all complex numbers Z such that the absolute value of Z is equal to 1. We can define a homomorphism phi from the additive group of real numbers R to T by phi of theta is sent to cosine of theta plus I sine of theta. Indeed, phi of A plus B equals cosine of A plus B plus I sine of A plus B equals cosine of A cosine of B minus sine of A sine of B plus I times sine of A cosine of B plus cosine of A sine of B is equal to cosine of A plus I sine of A times cosine of B plus I sine of B is equal to phi of A times phi of B. Geometrically, we are wrapping the real line around the circle in a group theoretic fashion. The following proposition lists some basic properties of group homomorphisms. Proposition 11.4. Let phi from G1 to G2 be a homomorphisms of group. Then, 1. If E is the identity of G1, then phi of E is the identity of G2. So we map the identity to the identity if we have a homomorphism. 2. For any element G in G1, phi of G to the negative 1 is equal to phi of G to the negative 1. 3. If H1 is a subgroup of G1, then phi of H1 is a subgroup of G2. 4. If H is a subgroup of G2, then phi to the negative 1 H2, which is equal to the set of all G of G such that phi of G is in H2, is a subgroup of G1. Furthermore, if H2 is normal in G2, then phi to the negative 1 H2 is normal in G1. Proof. For 1, suppose that E and E primes are the identities of G1 and G2 respectively. Then, E prime phi of E is equal to phi of E is equal to phi of E times E is equal to phi of E times phi of E. So by cancellation, on the right, we have that phi of E is equal to E prime. 2. This statement, the statement that for any element G in G1, phi to the G negative 1 equals phi of G to the negative 1, follows from the fact that phi to the G to the negative 1 times phi G equals phi of G to the negative 1, G, equals phi of E, equals phi of E to the phi of E prime. So then we just multiply both sides by phi of G to the negative 1, and we get our desired result. 3. The set phi of H1 is non-empty since the identity of G2 is in phi of H1. Now, suppose that H1 is a subgroup of G1 and let X and Y be in phi of H1. Then there exist elements A, B in H1 such that phi of A of X equals X and phi of B equals Y. Since XY equals phi of A, phi of B to the negative 1 equals phi of A, B to the negative 1 is in phi of H, then phi of H is a subgroup of G2 by proposition 3.31, which is a statement saying that if X times Y to the negative 1 is in your subgroup for any elements X and Y in your subgroup, then your subgroup is closed under multiplication as need be. And we also show that it's non-empty. 4. Let H2 be a subgroup of G2 and define H1 to be phi to the negative 1 H2. That is, H1 is a set of all G in G1 such that phi of G is in H2. The identity is in H1 since phi of E equals E prime. If A and B are in H1, then phi of AB to the negative 1 equals phi of A, phi of B to the negative 1 is in H2 since H2 is a subgroup of G2. Therefore, AB to the negative 1 is in H1 and H1 is a subgroup of G1. If H2 is normal in G2, we must show that G to the negative 1 HG is in H1 for H and H1 and G in G1. But phi of G to the negative 1 HG is equal to phi of G negative 1, phi of H, phi of G, which is in H2 since H2 is a normal subgroup of G2. It was one of the equivalent conditions for a group to be a normal subgroup. Therefore, G to the negative 1 HG is in H1 and H1 is normal. This is actually going to be of particular importance. Let phi from G to H be a group homomorphism and suppose that E is the identity of H. By proposition 11.4, phi to the negative 1 E is a subgroup of G. This group is called the kernel of phi and will be denoted by kernel of phi. So we'll write, let me just like smush all these notes on the right a bit. So kernel of phi is equal to the set of all G in G such that phi of G equals E in G2 or in H with how I'm writing it in H. So in fact, this subgroup is a normal subgroup of G since the trivial subgroup is normal in H. We state this result in the following theorem, which says that with every homomorphisms of group, we can naturally associate a normal subgroup. Theorem 11.5. Let phi from G to H be a group homomorphism. Then the kernel of phi is a normal subgroup of G. Example 11.6. Let us examine the homomorphism phi from GL2R to R star defined by A is sent to the determinant of A. Since 1 is the identity of R, the kernel of the homomorphism is all 2x2 matrices having determinant 1. That is, kernel of phi is equal to SL2R. Also, this should note some very powerful applications of this. Proving that SL2R is normal Normally it isn't that hard, but it's a bit tricky. And if you already don't know about multiplication of determinants, it can be kind of a nightmare. However, just knowing that kernel of phi is like SL2R, and it's the kernel of some homomorphism, we already know the group is normal without doing any extra work. Example 11.7. The kernel of the group homomorphism phi from R to C star, defined by phi of theta equals cosine of theta plus I sine of theta, is 2 pi n for n in Z. Notice that the kernel of phi is isomorphic to Z here. This is going to be a very big thing, just saying. Example 11.8. Suppose that we wish to determine all possible homomorphisms phi from Z mod 7 to phi mod 12. Since the kernel of phi must be a subgroup of Z mod 7, there are only two possible kernels, 0 and all of Z sub 7. The image of a subgroup of Z sub 7 must be a subgroup of Z sub 12. Hence, there is no injective homomorphism. Otherwise, Z sub 12 would have a subgroup of order 7, which is impossible. Consequently, the only possible homomorphism from Z sub 7 to Z sub 12 is the one mapping all elements to 0. Example 11.9. Let G be a group. Suppose that G is in G, and phi is a homomorphism from Z to G, given by phi of n is equal to G to the n. If the order of G is infinite, then the kernel of this homomorphism is 0, since phi maps Z onto the cyclic subgroup of G generated by G. However, if the order of G is finite, say n, then the kernel of phi is nz. 11.2. The isomorphisms theorem. Theorems. This is going to be good. Although it is not evident at first, factor groups correspond exactly to homomorphic images, and we can use factor groups to study homomorphisms. We already know that with every group homomorphism phi from G to H, we can associate a normal subgroup of G, kernel of phi. The converse is also true. That is, every normal subgroup of a group G gives rise to a homomorphism of a group. Let H be a normal subgroup of G. Define the natural or canonical homomorphism phi from G to G over H by phi of G is sent to GH. This is indeed a homomorphism since phi of G1 G2 equals G1 G2H equals G1H G2H equals phi of G1 phi of G2. The kernel of this homomorphism is H. The following theorems describe the relationship between group homomorphisms, normal subgroups, and factor groups. Alright. The first isomorphism theorem, theorem 11.10. If psi from G to H is a group homomorphism with K equal to the kernel of psi, then K is normal in G. Let phi from G to G over K be the canonical homomorphism. Then there exists a unique isomorphism, eta, from G over K to psi of G, such that psi is equal to eta phi. So let me be very clear about this, because this is a very complicated thing. So we're going to have, as our setup, we have G, and we have some homomorphism G to H, some homomorphism phi. Actually, no, they write it as psi, so I'll write it as that. So we're going to have psi from there. Then we're going to have G over the kernel of psi. Then we're going to have a canonical map here. Now note that we can actually kind of expand this out a little bit. Psi isn't really mapping to H. Psi is mapping to psi of G. Which is then mapping under inclusion to H. So we have this psi of H is psi of G is a subgroup of H, but because we don't really care about that, we don't really care about stuff that's not in that, it's all good. So let me also, in that case, fix this angling. So G over kernel of psi. What we're saying is that they're basically, we're saying that there exists a unique, we write it eta, such that this diagram commutes. So what do we mean when we say that this diagram commutes? We say that psi is equal to eta phi. And eta is an isomorphism. So another way to think about the commutivity of the diagram is that from G, we can get to psi of G in two different ways. We can either go through that, or we can go through phi, and we can go through an isomorphism here. And strictly, we should be sending it to H, but the thing is we're only worrying about the image of psi. So, proof. We already know that K is normal in G. Define eta from G over K to C of G by eta of GK equals C of G. We first must show that eta is a well-defined map. If G1 equals K equals G2 of K, then for some K in K, G1 of K is equal to G2. Consequently, eta from G1 of K is equal to C of G1 is equal to C of G1 C of K, because remember C of K is mapped to the identity, equals C of G1K is equal to C of G2 is equal to eta of G2K. Thus, eta does not depend on the choice of coset representative, and the map eta from G over K, the psi of G, is uniquely defined since psi is equal to eta phi. We must also show that eta is a homomorphism. Indeed, eta from G1K, G2K equals eta of G1, G2K is equal to C of G1, G2 is equal to C of G1 times C of G2 is equal to eta of G1K, eta G2K. Clearly, eta is onto psi of G, because if we want to have suppose we have some phi of G, then we just let it be that coset GK, and then we have onto. To show that eta is 1-to-1, suppose that eta G1 of K equals eta G2 of K. Then phi of G1 equals phi of G2. This implies that psi to the G1 to the negative 1 G2 is equal to E, or G1 to the negative 1 G2 is in the kernel of psi. Hence, G1 to the negative 1 G2 of K is equal to K. That is, G1 of K is equal to G2 of K. Mathematicians often use the following diagrams, called in this case commutative diagrams, to describe such theorems. The following diagrams commute since eta equals psi phi. So let me write out this, and let me write out a visual kind of flow interpretation. So we have G, H, we have this homomorphism C, and we have G over the kernel of C. So phi, eta. There exists a unique eta. So for now, what this is saying is that we have psi and phi predetermined. And what this diagram is saying is that we can fill in on the diagram from G over kernel of psi to H such that it's commutative. What does it mean that it's commutative? Well, in this case, it means that we have two paths to get from G to H. We can either go straight to H using psi, or we can follow phi and then go up eta. And what it's saying is that these two paths are functions, and these two functions are equal. So from here, using this diagram on the left hand side, G, we can either go straight from G to H under psi, or we can go from G to G over K, then from G over K to H, using psi and then eta, which remember, because we're working with functions, we write it as we go to psi first, then we go to eta, but we write eta on the left, because it's function composition notation. Example 11.11. Let G be a cyclic group with generator G. Define a map phi from Z to G by n goes to G to the n. This map is a surjective homomorphism. since phi of m plus n is equal to g of m plus n equals g of n is equal to phi of n. Clearly, phi is onto. If the order of g is equal to m, then g to the m is equal to e. Hence, the kernel of phi is equal to mz, and z over the kernel of phi is equal to z over mz is isomorphic to g. On the other hand, if the order is infinite, then kernel of phi is equal to 0, and phi is an isomorphism of g and z. Hence, two cyclic groups are isomorphic exactly when they have the same order. Up to isomorphism, the only cyclic groups are z and z sub n. So yeah, this is one of the examples of like homomorphisms allow you, by studying the relations between objects, tells you a lot about the objects themselves. So, okay. Theorem 11.12, the second isomorphism theorem. Let H be a subgroup of group G, which is not necessarily normal in G, and N a normal subgroup of G. Then Hn is a subgroup of G. H intersected with N is a normal subgroup of H. Notice here, H sub n is a normal subgroup of H. And H over H cap n is isomorphic to Hn over n. So let me write that all out again, because this is a fair amount. So we have H as a subgroup of G, not required to be normal, not required to be normal, and is a subgroup of G, is normal. So we have that our theorem is that H over H cap n is isomorphic to Hn over n. So for this isomorphism theorem, notice that we have Hn over n. We're really talking about the universes of H and Hn specifically. G is just kind of an ambient group in which H and Hn live, in this specific case. Proof. We will first show that Hn equals H times n, H and H and n and n is a subgroup of G. And this is actually, to show that this is a subgroup, we specifically needed that, since we are not assuming G is abelian, that n is a normal subgroup of G. You'll see why. Suppose that H1n1, H2n2 is an Hn. Since n is normal, we know that H2 to the negative 1, n1, H2 is an n. So, H1n1, H2n2 is equal to H1, H2, H2 to the negative 1, n1, H2, n2 is an Hn. The inverse of Hn, which is an Hn, is an Hn, since Hn to the negative 1 equals n to the negative 1, h to the negative 1, equals h to the negative 1, hn to the negative 1, h to the negative 1. Next, we prove that h cap n is normal in H. Let H be an n, H and n be an H cap n. Then, h to the negative 1 nh is an H since each element is an H. Also, h to the negative 1 nh is an n since n is normal in G. Therefore, h to the negative 1 nh is an H cap n. Now, define a map phi from H to Hn over n by H is mapped to Hn. The map phi is onto, since any coset h and n is equal to Hn is in the image of H. We also know that phi is a homomorphism, because phi of hh prime equals hh prime n equals hn h prime n equals phi of h prime. By the first isomorphism theorem, the image of phi is isomorphic to H over the kernel of phi. That is, Hn over n is equal to phi of H is isomorphic to H over the kernel of H. Since the kernel of phi is equal to H and H, along with H and n, which is equal to H cap n, then Hn over n is equal to phi of H is isomorphic to H over H cap n. Notice that was very technical, but we define a homomorphism from H to Hn over n, and then from that homomorphism and the first isomorphism theorem, we're able to determine that H over kernel of phi is a normal subgroup, and there's an isomorphism there. And from there, or unique isomorphism even. And from there, we have that h over kernel of phi is equal to h over h cap n, which gets us the actual result here. This is more so a representation that h over kernel of phi is mapped to this, but it's just in this case that the kernel of phi is a set of all elements that are in h and n. Alright, so this is a theorem I actually had a fair amount of difficulty with, so it's good to review this. So theorem 11.13, the correspondence theorem. Let n be a normal subgroup of a group G. Then h is mapped to h over n is a one-to-one correspondence between the set of subgroups h of G containing n and the set of subgroups of G over n. Furthermore, the normal subgroups of G containing n correspond to normal subgroups of G over n. So one more time, I'm going to put this on the board. So if n, so suppose n as a subgroup of G is normal. Then there's a one-to-one correspondence, or a bijection, which maps h to h over n. Alright, right? H over where, let's call this map phi, where domain of phi is the set of all subgroups of G containing n. So basically, if we have a normal subgroup of a group n, then mapping each group to the factor group under that specific set as its domain, we establish a bijection. So every group, a subgroup, is uniquely sent to a factor subgroup, and every factor subgroup corresponds exactly to a subgroup that's sent to it. I'm just putting that here because it doesn't talk about things in terms of phi. It uses some mathematical writing that's obviously emblematic of someone who's more in the theory side, where we actually don't describe the name of the function. We just describe what the function does, and then we describe the actual domain and range of it. Proof. Let H be a subgroup of G containing n. Since n is normal in H over n is a factor group. Let an and bn be elements of H over n. Then an b to the negative 1n equals ab to the negative 1n is an H over n. Hence, H over n is a subgroup of G over n. So this first of all establishes that we do have a valid range that sends our subgroup H's of G's to actual subgroups of G over n. Let S be a subgroup of G over n. The subgroup is a set of cosets of n. If H is equal to the set G and G, such that Gn is an S, then for H1, H2, and H, we have that H1n, H2s is equal to H1, H2 of n is equal to is an S, and H to the negative 1n is an S. Therefore, H must be a subgroup of G. Clearly, H contains n. Therefore, S is equal to H over n. Consequently, the map H being sent to H over S, H over n is onto. A lot of this, also note, the important thing to note is that S is a subgroup, and that's why we can assume a lot of this in this paragraph. Alright, now, suppose that H1 and H2 are subgroups of G containing n, such that H1n is equal to H2n, so we're proving injectivity with this. If H1 is an H1, and H1n is an H1 over n, then H1n is equal to H2n as a subset of H2 for some H2 and H2. However, since n is contained in H2, we know that H1 is an H2, or H1 is a subset of H2. Similarly, H2 is a subset of H1, which shows us that H1 is equal to H2, because what it means for these two sets to be equal is that they both contain each other. Since h1 is then equal to h2, the map h from h over n is 1 to 1. Suppose that h is normal in G, and n a subgroup of h. Then it is easy to verify that the map G over n to G over h, defined by Gn, sent to Gh, is a homomorphism. The kernel of this homomorphism is h over n, which proves that h over n is normal in G over n. Conversely, suppose that h over n is normal in G over n. The homomorphism given by G is sent to G over n, is sent to G over n over h over n, has kernel h. Hence, h must be normal in G. So yeah, this correspondence theorem is a lot, and it uses a lot of words, not a lot of notation. So if you want to second pass that, and you're watching the video, rewind, do not be afraid to look through the whole thing a second time, because there's a lot of details, and it's very technical. Alright, notice that in the course of the proof of theorem 11.13, we have also proved the following theorem, which this is because this has kernel h. So the third isomorphism theorem, let G be a group and n and h be normal subgroups of G with n as a subset of h. Then G over h is isomorphic to G over n over h over n. So example 11.15. By the third isomorphism theorem, z over mz is isomorphic to z over mnz over mz over mnz. Since the order of z over mnz is equal to mn, and z over mz is equals m, we have that mz over mnz is equal to n. Alright, so, not worrying about stage because no. Reading questions. Let me clear the board for this. Consider the function phi from z10 to z10, defined by phi of x is equal to x plus x. Prove that phi of x is a group homomorphism. So phi of x plus y equals x plus y plus x plus y is equal to x plus x plus y is equal to phi of x plus phi of y. More generally, this holds with any homomorphism phi defined by that from G to a group, from a group G to a group A, with A abelian. And the important abelian thing here is when we were able to swap these, we needed that abelian process. Alright, for phi defined in the previous question, explain why phi is not a group isomorphism. So we see that phi is not onto. So phi of n plus n is equal to, no, phi of, my bad. Phi of n is equal to n plus n is equal to 2n. Which means that the image of phi is equal to the group generated by 2 as a strict subset of Z mod 10. So you'll never hit an odd number with this defined homomorphism. So it will never be surjective. It's actually not even injective because of that, but we'll not worry about that. Compare and contrast isomorphisms and homomorphisms. So isomorphisms are both one-to-one and onto, but also there's a better way of describing an isomorphism. So for any isomorphism, phi, there's a isomorphism phi, we call it phi to the negative 1, such that phi to the negative 1 equals phi to the negative 1 phi equals the identity. And it's important to note that these two conditions are non-trivially different. So like any injective function will technically have a function back to it that will send it like back to where it came from. But if it's not surjective, then if you try to do it in the reverse direction, then there'll be certain elements that'll be restricted. Because the image of phi in this case would not be the entirety of h. So no function from h to g would then, when you compose it with that, be sent back there. This is a useful way that we actually define isomorphisms category theoretically. We look for this requirement. We have some identity error, and we require that phi to the -1 equals phi to the -1 phi is equal to the identity, that identity error. Category theoretically, you would say every isomorphism in that is an epi and monomorphism, although that's strictly in the category group, but that's like getting unnecessarily semantic-y. Paraphrase the first isomorphism theorem using only words, no symbols allowed at all. So basically, if we have a homomorphism phi to h, first of all, let's just restrict that homomorphism to just make it phi from g to like phi of g. Then that homomorphism, taking the kernel of that homomorphism, is normal. So for give me a second. Apologies for that, but the first isomorphism theorem can be thought of as if we have some homomorphism from one space to another, then there is a associated isomorphism from that group to the image of the homomorphism with g over the kernel of that space, or g over the kernel of that transformation. 5. For every normal subgroup, there's a homomorphism, and for every homomorphism, there is a normal subgroup. Explain the precise basis for this fig statement. So basically, if you have a normal subgroup, then there will be some space that has a homomorphism to itself. Oh, I'm trying to remember the precise way to say this. Oh wait, I'm trying to actually properly think. Yeah. So if you have a normal subgroup, then if you take the image of it to its factor group, then there'll be a homomorphism of that with kernel, that normal subgroup. And every homomorphism, every surjective homomorphism, corresponds uniquely because of that kernel of phi to a unique normal subgroup. Alright. Yeah, alright, proving the exercises. Before I prove the exercises, just gotta quick do some things, so intermission time. Alright, I am back, and I'm ready to go. Shh. Alright. Oh gosh, why is my Chrome working like this? Alright, this is page 148, right? I'm gonna need a quick second to refresh the Chrome page. Also, I saw that there was a viewer, I don't think they're here now still, who pointed out some ambiguity. There could possibly be ambiguity in my explanations that would like no doubt be of no surprise to me, because my explanations are just like very vague for the review. But let me just check where it is. All right, so yeah, when I say one-to-one, I mean that injective. So just to clarify this now, a function is one-to-one if f of a being equal to f of b implies that a is equal to b. So you don't have two elements that are different being sent to the same element. Onto means surjective, which means that for every element in the space that we're mapping to, so f of a to b is onto, if for every b and b there's some a and a, such that phi of, or not phi, I've been using too many phi's today, such that f of a is equal to b. Besides that, I know the viewer had also asked how is g to the negative 1 defined, and it's probably always good to go through this, because I kind of just assume everyone's been like watching the whole group theory thing, but they haven't been. So in our elements, in our group, like we have some group G circle. I'm going to at least assume you know what a group is. Then for every element G in G, G to the negative 1 is the unique element, such that G to the negative 1 is equal to G to the negative 1. G is equal to the identity. So G in this case is not a function. G is an element. Sometimes when we're talking about elements as functions, we'll call G a function, but like that's a very specific case. That isn't what we're generally going for. Okay. So, anyways, on to exercises. Let's actually take my sweet time scrolling through these. Give me a minute. Alright, reading questions, exercises. So, prove that. So, first of all, we proved this in a previous exercise, and it was a bunch of painful algebra, so I'm not going to worry about it. You can just assume one is already proven. So 2, which of the following maps are homomorphisms? If the map is a homomorphism, what is the kernel? So A is phi of r star to GL2R, defined by phi of A is equal to 1, 0, 0, 1. So, okay. So 1, 0, 0, A. AB is equal to, it's very easy to just do the math on this, 1, 0, 0, A, 1, 0, 0, B. So phi of AB is equal to that, is equal to that, is equal to phi of A, phi of B. So it shows that it's a homomorphism. Its kernel in this case is the one element that is sent to 0, 0, 0, 1. So the pre-image of this is the kernel, so phi to the negative 1 kernel of that, which in this case is literally just equal to the single element 1, one of the two trivial subgroups of R star. Also, we know this is well defined, by the way, because remember, we're working in R star, so we don't have 0 in R star. We don't have that, we call it absorption element. Alright. B from phi of R to GL2R defined by phi of A is equal to 1A, 0, 1. I'm thinking that this might not actually be well defined. Yeah, this doesn't look like it's going to be well defined. Because, like, let's think about it. So 1A, 1, 0 times 1B, 0, 1. Actually, it might be. I might just be, like, wrong. Oh, yeah, it is actually well defined. Yeah, I was just being dumb. Is equal to So we have 1 plus 0. We have 0 plus 0, so we have 0 there. We have a plus b. Oh wow, we actually, alright, that's nice. A plus b and 1 there. So we actually have we don't have, wait, let me think about this for a second. Oh yeah, we actually do have a well-defined homomorphism. Oh, not actually a homomorphism. We nearly have a homomorphism. Oh no, actually we do, yeah. Why am I like really off my game today? So, because this is equal to phi of a, phi of b is equal to phi of a plus b, we have a homomorphism, and the kernel is the pre-image of 1, 0, 0, 1, which is equal to, again, the trivial subgroup. There's definitely a whole like matrix thing going on here. Phi of GL to R defined by phi of A, B, C, D is equal to A plus D. Let's see. So phi of A, B, C, D, E, F. Actually, instead of doing E, F, G, H, because that's horrible, I'll do A prime, B prime, C prime, D prime is equal to phi of A prime plus B, C prime. Then we have A, B prime. A, B prime, right? Let me think. Oh gosh, my brain is failing me. A, B prime plus B, D prime plus D prime. Yes, brain, please work again. Then we have C, A prime plus D, B prime. And we have C prime, no, not C, CB prime, CB prime plus D, D prime. So phi of that is equal to A prime plus BC prime plus CB prime plus D, D prime. Which is not a homomorphism because is not equal to, it's not equal to A plus D plus A prime plus D prime. There are some factors here which are not included in the original factors. And if we have a nice subset, then yes, it will be included. It will work as that, but in this particular case, it will not work. So we have it's not a homomorphism. So phi of GL2R to R star. This is the determinant of that matrix, and because of the multiplicity of the determinant and the fact that it goes to positive values, it's true. And the inverse of 1, this, I think actually this was an example that went into the text. The kernel of the set of determinant 1 matrices is the set of matrices of determinant 1, which is just SL2 by 2R. And then phi is the additive group of 2 by 2 matrices with entries in R. If it's the additive group, then this is actually a homomorphism. And its kernel is the set of matrices of the form ABC 0. So it's a set of all lower triangular matrices. So 3. Let A be an m by n matrix. Show that multiplication, matrix multiplication x to ax defines a homomorphism phi from Rn to Rm. This is because if A is an n by n matrix, we have that A of n plus m equals A of n plus A of m. This comes down to the fact that matrices are linear like transformations. And this is like fundamentally minus the scalar part, what we mean for like linear transformations to, be linear transformations. I'm going to assume you've read a linear algebra book. Let phi from z to z begin by phi of n is equal to 7n. Prove that phi is a group homomorphism. Find the kernel and image of phi. So the image of phi. The image of phi. Oh yeah, this has... Okay, so basically, the kernel of phi is still equal to 0 because it's sending every non-zero element to a non-zero element. But the image of phi is 7z. So in a sense, this also gives an isomorphism z to 7z. All right. Describe all homomorphisms from Z24 to Z18. Okay. So phi, suppose phi is a homomorphism from Z24 to Z18. First, let's find the factorized forms. So 2 times 12 equals 2 times 2 times 2 times 3. And for 18, we have 2 times 9, which is equal to 2 times 3 times 3. So if phi is a homomorphism, I'm wondering if all homomorphisms from Z24, not even Z24, all homomorphisms from Zm to Zn take the form of like some k times, take the form of some k times n or k times, actually wait, let me write it out. Phi of q is equal to k times q mod n. I'm wondering if all homomorphisms will actually take that form. So let's think. So let's suppose that phi, I think it will, yeah. Because phi of m is going to be equal to phi of 1 plus 1 plus on and on plus 1 m times is going to be equal to phi of 1 plus phi of 1 plus all the way up to plus phi of 1 m times. So every homomorphism, well, it's more so this is generally true of cyclic groups, from Z mod n to Z mod m are determined by where 1 is sent. What is sent? Alright, so let's think more so about what this informal property tells us about the transformations. So we'll make a notation. So we're going to be calling the transformation A transformation, we're going to be using this notation. Phi m n k is a homomorphism Zm to Zn such that phi of 1 is equal to k. So let's think a fair bit carefully about how this is defined. Yeah, so phi m n k. So first of all, phi of m times 1 equals m times phi of 1 is equal to 0, which implies that m times k is equivalent to 0 mod n. Where m is fixed. So we know that let me think about what this specifically means. So k not the least common multiple. So like z mod 4 to z mod 2. We know that k can't be even. So we know that k must divide n. So we know that k must divide n, first of all. But we can get more specific than that. We simply must have that n divides k of m, n divides km. So let's, okay. Also, thinking about this, I mean, would this uniquely, if m times k is equivalent to 0 mod n, does this define all homomorphisms? We know that this must be true of a homomorphism, but if we can find a k such that m times k is equivalent to 0 mod n, I think so. Because then phi of p plus q is equal to kp plus kq is equal to phi of p plus phi of q. Now, I'm trying to think about what I want to how I specifically want to say this. Because I think this should uniquely describe it, but I want to make sure I'm not doing something kind of daft. So okay. Because we can easily define phi with the representatives. but it doesn't mean we're going to have a homomorphism. So it's more so about well-defining things. Oh, okay, I think I know how to show it's well-defined. So phi of p plus phi of m plus p is equal to kp plus km plus kq. And because this is equivalent to 0, because of this condition right here, this is going to be equal to kp plus kq. Otherwise, if km is not equal to 0, then when we move up, when we kind of move up in oscillation, if that's how you want to say it, then we're going to have a non-defined or a non-well-defined structure. Yeah, I guess one of the conditions on this is that like phi of 0 should equal phi of m, which implies that 0 plus k is equivalent to 0 mod n. Mk is equivalent to 0 mod n, which implies that mk is equivalent to 0. So every homomorphism can be defined by an integer k, such that m times k is equivalent mod n. So let's think about all the, let's make a k table, we'll call it, for, what were our examples? Not z by z. Describe all homomorphisms from z24 to z18. 24 to 18. Okay. So we know that 24 is 2 times 2. 12 divided by 2, we get 12, we get 2 times 3. And 18 is going to be 2 times 3 times 3. So we know that mk is equivalent to cn, right? Or equals cn. 2 times 2 times 2 times 3. K is equal to some c. We're going to also not worry about the 0 case, or actually not, at least not immediately. Is equal to 2 times 2 times 3. 2 times 2 times 3. Or 2 times 3 times 3, my bad. 2 times 3 times 3. Which means that we divide 1, we take out 1, 2, and we take out 1, 3. 1, 2, take out 1, 3. So we get that 4k is a multiple of 3. Or at least, yeah, to a reasonable. So we have k is equal to 0. For a 12, 12 is a valid number. So k is equal to 3. And actually, because these numbers are co-prime, it'll be that all the way up to the first. So we're going up to 18. So k is all multiples of 3 up to 15. So all these uniquely describe all possible homomorphisms between z sub 24 and z sub 18. Sick, okay. That was actually like one of the times I've had to like apply a new method of research that I haven't seen in this book yet. And that was actually a really satisfying thing to do. So, describe all homomorphisms from Z to Z12. Oh, simple. So basically, Z sub 1 will have some finite order. Or like if there is a homomorphism, so phi from z to z mod 12, since 12 times phi of 1 equals 0, we have that, or well, actually 12 times phi of k equals 0 for any k. We know that phi of k needs to be equal to 0. So the only homomorphism is the 0 homomorphism, which sends every element to 0. Alright, in the group, let's see, let's say John. Yeah, nah, I'm good. Because it's very computational. When it's talking about the second isomorphism theorem. If G is an abelian group and n is an n, show that phi from G to G divided by G to G to the n is a group homomorphism. So, okay, the reason we need G to be an abelian group here, just in case you don't get why G has to be abelian. So phi of xy, we'll call it phi n of xy equals xy to the n. We don't necessarily have to have our group be strictly abelian for this to be the case. Like, there are some weird pathological exceptions we can actually have. But normally, if G is abelian, we know for sure that we can actually bring out that n like this. So it's equal to phi n x phi n y. Alright, delete. If phi of G, phi of G, oh wait. If phi of G to H is a group homomorphism and G is abelian, prove that phi of G is also abelian. This is actually not an insignificant exercise. So suppose that we have elements x, y. Suppose phi is abelian. I'll write phi is abel. And we have like x, y in phi of G. So this means that there are elements A and B in G with phi of A equals to phi of B. Then from here, xy, the product xy, is equal to phi of A, phi of B is equal to phi of AB. I shouldn't put a comma there. What am I doing? I'm a fool. Equals phi of BA is equal to phi of B, phi of A is equal to yx. So notice that we require, for this step right here, we require that our group G is abelian. Or no, I shouldn't say phi is abel. That's me being silly once more. So G is abel. And note that specifically what this says is that the image of an abelian group corresponds to an abelian subgroup. So we can only kind of map out the elements in another group with an abelian group up to a kind of abelianness. It's a really nice way of actually proving that there cannot be an isomorphism between a abelian group and a non-abelian group. If phi of H is group homomorphism and G is cyclic, prove that phi of G is... It's a similar logic to 10, so I'm not going to reiterate that. Prove, show that a homomorphism is defined as cyclic loop is completely determined by its action of the generators. That's another very simple thing. If a group G has exactly one subgroup H of order K, prove that H is normal in G. Actually, wait, wasn't this literally the same thing? Shh. Because if I remember correctly, if G has exactly one subgroup H of order K, prove that H is normal in G. you basically show that if there's more than one, we have some like third group, or if we have that H is not normal, then we have some second subgroup of order k. Yeah, that was literally the last exercise, last chapter. So okay, prove or disprove. The rationals over the integers are isomorphic to the rationals. So every element is of the form. Wait a minute, I'm wondering. So P over Q. Oh no, get rid of all that. That's old work. P over Q plus Z. So what we need is Q over Z. So if we can find some homomorphism, Q to Q. So using the first isomorphism theorem, we should be able to find a homomorphism Q that maps to Q with kernel Z. Let me think. Like, intuitively, I'm feeling that it wouldn't be true, but weirder things are true. Especially because we're working with infinite groups in these. Q over Z. So let's think. So first of all, we know that P over Q plus Z plus R over S plus Z, because we're working additively, not multiplicatively, is equal to PS plus RQ over QS plus Z. What I'm wondering, what I'm thinking here, let me move up a little bit, kind of check out this. So I'm wondering, are the integers, I feel like the second isomorphism theorem would imply that if the integers were normal, the rationals cap the integers is just the integers. So the rationals over the integers is isomorphic to, that's the same thing, yeah, man. Also, this is being particularly tough. So we have this structure. Now what I'm thinking is that So if there is some phi from Q over Z to Q, that would imply that I'm trying to think of how one would disprove this. Because my inherent thought is disproof. So the interest let's see. So if we add that So let's think. So phi of P over Q plus, I'll just use this notation. It doesn't mean plus or minus, it's just because I don't want to have to write out the plus C. So whenever I'm writing this, just imagine we're writing a plus C. Equals phi of 2p over Q. Oh, okay. I think I got it. Okay, so suppose that there was some isomorphism. It must send P over Q with P and Q not equal to 0 to a non-zero element. Otherwise, it would have a non-trivial kernel, which would imply that we would not have an injective map. However, if that were the case, we add P over Q to itself Q times, and we have we go back to 0. However, by what phi must be, it's just that multiplied by itself Q times, which isn't 0. We would technically say because the rationals are not an integral domain. Which means that such an isomorphism cannot exist. Okay. So that comes down to another thing like multiplying something itself a certain amount of times to become an element of another group. Kind of like some almost cyclic element. That is what that phenomenon is intrinsically capturing. That makes it not isomorphic. So okay, let you be a finite group and subgroup G. If H is a subgroup G over N, one of H is a subgroup of order is a group of G is a group of order H times N, where phi from G to G over N is a canonical homomorphism. Okay. So, I guess one way I can write this is that phi to the negative 1 of H equals, because each coset is disjoint, or because each coset, we're unioning cosets in the preimage, is the union of the order of n, because each coset is the same the order of phi to the negative 1 is we multiply by the number of, we multiply for every a and h, the cardinality of the number of cosets n, because each coset is both disjoint and equally sized compared to each other, which is just equal to the order of h times the order of n. Fundamentally, certain elements with respect to it represents. That's the rough intuition for that. Okay. Let G1 G2 be greater than G1 G2, respectively let G1 G2. So homomorphism G bar of G1 to H1 to G bar H2 if phi of H1 is a subset of phi of H2. So let's think. So if we have H1, we have an inclusion to G1. We have a homomorphism phi to G2. And we have a second group 2i with phi of H1 is a subset of H2. So there's a homomorphism G1 over Gi H1 to G2 over H2. So what we have here is we have G1 mapping to G1 over H1, which maps to G2, which maps to G2 over H2. We can actually even write this all out. So with the language they used previously, we have phi, c, eta. Oh, that's the worst eta I've ever drawn. And we have phi prime. So we have this, and we want to show that there is a homomorphism induced. Phi of H1 is a subset of H2. I'm wondering what it's more so specifically asking. Let G1 to G2 be a homomorphism. Show that phi induces a homomorphism of G1 over H1 to G2 over H2. Oh, to show that it's well defined. Okay. So we let phi2 phi prime be from G2 to G2 over H2, and define okay, now I know what I was saying. I was putting the cart before the horse there, because we don't know that H is necessarily the kernel of something. So we define phi from G1 over H1 to G2 over H2. Or yeah, define phi bar. Alright, so we're gonna let me write this down formally. Let phi be from G1 to G2. G1 to G2. Where we have phi bar of A plus or A H1 is sent to phi of A, H2. So we need to show that this is well defined. So suppose that A H1 is equal to B H1. Wait, I'm thinking actually. So A H1 is equal to B H1. So, and suppose we have phi of A. Wait a minute, let me think. Which means that for AH, there exists an H prime such that BH prime. So suppose we want to show that phi A of H2 is equal to phi of B of H2. So for that, phi of A, suppose we have some phi of A H. Phi of A H1, we call it H1 prime, H2, H2 prime. This is weird. Okay. I'm definitely just missing something simple, but okay. H1 is equal to H2 is a subset of H2. Yeah, so we need to find some H prime 2 such that phi of B is equal to H10 2. So phi to the negative 1, A, B to the negative 1, AB. So we have that phi to the negative 1. Actually, strictly speaking, it should be phi to the negative 1 BA. We're looking for some H prime such that phi to the negative 1 H2 equals phi to the negative 1 H2 prime. So phi to the negative 1 BA. Well, because of homomorphisms, we know that phi to the negative 1 BA is in, it's in H1. Which implies that because phi of H1 is a subset of H2, shows us that we can just let H prime prime be equal to phi of, why am I doing that? Phi negative 1 B5. B negative 1A, or actually we can say that to the negative 1, we can let phi h prime equal phi to the negative 1 that, which is actually in h2. Because we know that phi of h1 is in, yeah, we know because b to the negative 1 is in that. Okay, that's actually nice. So that shows us that it's well defined, that the cosets correspondingly to the same, well, one way we can say it's well defined is that the cosets that correspond to the same element, showing that they're the same is showing that if you take the inverse of one, it will give you back 0. Okay, that's actually nice. If h and k are normal subgroups of G, and h cap k is equal to E, prove that G is isomorphic to a subgroup of G over H times G over K. If h and k are normal subgroups of G, and h cap k is equal to E, prove that G is isomorphic to a subgroup of G over H, G over K. I think it's going to be something second isomorphism theorem related. Because the second isomorphism theorem, yeah, H times K in this case would be equal to G. Oh, wait, no, not necessarily. So we know, let me write this down. H over H cap n is isomorphic to Hn over Hn over n. Wait, let's think about this harder. If h and k are normal subgroups of G, and h cap k is equal to E, prove that G is isomorphic to a subgroup of G over H times G over K. So what we can do is we can define a map G. Oh, alright. G over K. This is first isomorphism theorem. Let's define this map. Oh yeah, they use eta. Let's define a map eta from G to G over H, G over K times G over H as follows. So any element can be represented as, because these groups are normal, and because they're, oh wait, let me double check. Oh, it's isomorphic to a subgroup. Okay. Wait, let me think a bit harder about this, because it's more so correspondence. So G over H times G over K. So I mean, we can send, we can just simply send A plus G to the map A plus K. We can just send A to A, it maps to A plus K, A plus H. This gives us our psi, this gives us a homomorphism. So we define psi by this. So psi is defined by, which means that we can map okay. Yep, that makes sense. Okay, so we then send phi to G over kernel of psi, which we map back to this. From G over kernel of C, kernel of psi to some subgroup of G over K of G over H. Now for this, notice, what would it mean for something to be in the kernel of psi? Well, it would mean both a plus k and a plus h is equal to 0. But if that's the case, that could only be the case if a is in k plus h. But k cap h is only equal to e. So we have g over kernel of psi is actually equal to g over e, which is isomorphic itself to g. So applying this isomorphism and then this isomorphism gives us an isomorphism of g to some subgroup of g over k times g over h. Alright, let phi from G1 be a surjective group homomorphism, let H be a null group, null subgroup G1, be a null subgroup G1, suppose that phi of H1 is equal to H2, H1 is isomorphic to G over H2. I'm assuming that this is going to be false, because we're not requiring it that it be injective. Also, I just realized something. All homomorphisms of Z to Z12. Oh, I was kind of dumb. Because you can just send Z of m plus n to k plus m times n. It's from Z mod something to Z that it actually fails the other way around. That was my bad. I just realized that my previous answer to this was wrong. You just need, literally any multiplication into Z mod 12, in which there are 12 such multiplications determined by where you send 1, is valid, a valid homomorphism. So there are 12 homomorphisms there. For this, an example we could use is we can let phi be, actually, you know what, on that topic, a bit of a redemption arc. Z to Z mod 12 be defined by just like phi of x is equal to x mod 12. Now, if phi of 2z, actually no, we need to choose a coprime factor. We have phi of 5z. The image of phi of 5z is actually equal to z mod 12. But obviously, z over 5z is not isomorphic to z mod 12 over z mod 12. So the theorem is false. And it comes down to the non-injectivity of it. So let phi from G to H be a group homomorphism. Show phi is a 1-to-1 if and only if the kernel is equal to E. So suppose that the kernel of phi contains two elements, A, B. Then this means that phi of A is literally just equal to phi of B. And done. But actually, a more specific thing is asking. It's basically saying that we can determine by the kernel. So suppose that phi of A is equal to phi of B. But, important to note here, but A is not equal to B. Then phi of A, B to the negative 1, is equal to E, which is equal to phi of 0. And since A is not equal to B, AB to the negative 1 is not equal to 0. Which means that the cardinality of the kernel of phi is greater than 1. That's something you'll commonly use in linear algebra. to check if a linear transformation is like injective, you literally only need to check that the kernel is like consists of only one element. Given a homomorphism by phi of A describe the equivalence classes. I'm assuming it's going to be something along the lines of equivalence classes. Because if phi of A is equal to phi of B, then first of all we have the coset of 0. Then we have the coset of like, yeah. So it's going to be cosets for this, it's going to be cosets of the kernel. So it's going to define the equivalence relation was actually give you the cosets of the kernel. Because if phi of A is similar to B, that means phi of A is equal to phi of B, which means that phi of A, phi to the phi of A b negative 1 is equal to 0. Which implies that AB to the negative 1 is in your kernel. So it will describe roughly at least the cosets of the kernel. Alright, instead of worrying about this, I'm actually way more excited for automorphisms, because automorphisms have to do with something called the Galois theory, which I'm intensely interested in and actually excited to be reviewing for. So 11.15, or not 11.15, I'm a fool, I'm a clown. 11.5, additional exercises, automorphisms. 1. Let aut of G be the set of all automorphisms of G, or isomorphisms from G to itself. Prove this set forms a group and is a subgroup of the group of permutations of G. That is, the automorphisms of G is a subgroup less than or equal to S of G. Mainly, it's going to be that since the composition of two isomorphisms is an isomorphism, and the inverse of an isomorphism is an isomorphism, then it trivially, like this theorem just kind of proves itself, and then because every isomorphism is a permutation, then that's where we get that. An inner automorphism of G, Ig, which sends G to G, is defined by the map Ig of x is equal to gx G to negative 1 for G and G. Show that Ig is in the automorphisms of G. So it's fine with that. So we basically want to show that Ig is in isomorphism. So suppose first of all, let's first show that it's onto. So suppose we have an element x, then applying g to the negative 1, x to g, let our input a be equal to that, then ig of a is going to be equal to g to the negative 1, x, g to the negative 1 is equal to x, so the inner automorphism is onto. To show that it's 1-to-1, if we have g to the negative 1 is equal to g to the negative 1, then by left cancellation we get a g negative 1 is equal to b g negative 1, and by right cancellation we have a is equal to b. So the automorphisms are both injective and onto. To show that they preserve the group structure, that's actually the big thing we need to show here. Ig of a b is equal to g to the negative 1 is equal to g to the negative 1, g to the negative 1 is equal to ig of a, ig of b. It's easy to show that the set of all inner automorphisms is defined by inner in G. First of all, the identity isomorphism is given by just letting G be E. To show that it's a subgroup, we have G to the negative 1, then A to the negative 1, or no. So we have this as being Ig. Actually, wait, let me write it properly. So we have Ig, A, IQ, not IQ, no, IH of A is equal to A G A G to negative 1 H A H to negative 1. Oh no, what am I thinking? I'm being dumb. That's not how you do this. Shh. So IG I H of A is equal to G H A H to negative 1 G to negative 1 is equal to IG IGH A, which implies that IG IH equals IGH, and obviously as well IG to negative 1 equals IE equals ID. So we have that these set of inner automorphisms are closed and contain the identity. Find G that is not an inner find automorphism of a group G that is not an inner automorphism. So yeah, okay. So let's say we have the automorphism of Z sub 5 that sends, so let's write it out as phi of Z sub 5 to Z sub 5, defined by phi of A equals 2A. Well, notice that this can't be an inner automorphism. Why? Because Z5 is abelian, and this isn't the identity. Now let's notice, if G is abelian, then IG of A equals G to the negative 1 equals, this step we can only take if G is abelian, G to negative 1, G to negative 1A equals A, implies the only automorphism the only inner automorphism, wait, let me say this. The only inner automorphism is the identity. However, we have some abelian group and we have some automorphism that is not equal to the identity. This means inherently that the automorphism cannot be inner. Alright, let G be a group and IG be an inner homomorphism G, and define about G goes to automorphism, G by G goes to IG, this is a homomorphism with image inner homomorphism kernel ZG. And kernel CG. Ooh. Oh wait. Also, yeah, this is actually, yeah, it's a cool proof. I like that. So, obviously, IGH equals GHA HG to the negative 1 equals IGIH, which put input A, which implies that IGIH, which implies that the map is an automorphism, which implies that phi is a homomorphism. And now, to prove that it has center ZG, ZG is defined to be the set of all, G, such that xg is equal to gx for all x and x. So suppose we have that. And this means, oh, because it's for all, we have that IG of A is equal to, we're assuming G is in this. g a g to negative 1, which by that abelianness, g to negative 1, a equals a, which is sent to the kernel, or the identity isomorphism, which by the first isomorphism theorem then, because it has image of all the, well, it just has the images all the inner automorphism, implies that g over z of g is isomorphic to the inner automorphisms of g. Which is really cool. The inner automorphisms of g can have a really weird structure to compute and write down, but g over z of g has a much more simple structure. Like an actually computable structure you can hold in your hands and don't have to observe whole functions at a time. Which also, as a reminder, I keep pushing this, but it is pushing this link between blurring the lines of objects and arrows, blurring the lines between objects and functions as objects, like to themselves be studied algebraically. Alright, compute the automorphisms of S3 and the inner of S3. Oh gosh, okay. So S3 contains the identity. We'll only be doing this for one case, because otherwise that'd be painful. So 1 3 1 2 1 3 1 2 3 1 3 2 1 2 1 3. Oh yeah, and we're missing 2 3. Let me just like close that bracket there. 2 3. So oh yeah, we're doing all automorphisms. So we know, because of like basic order considerations, that the elements will be shuffled around as followed. The identity will be sent to itself. Then each 1 2 1 3 2 3, these will be shuffled around with each other. And finally, so these will be shuffled around with each other. And finally, 1 2 3. Ooh, wait, I wonder if this means anything. 1 2 3 will be shuffled around with 1 3 2. Knowing this, let's think about what this would imply. I guess we should also write it out. I will also write this out in its corresponding this notation, because this will actually be very important. It will come in handy. 2 3. Oh no. 1 3 2 1, and then we'll have 1 2 1 3. So if phi sends 1 3, if it sends 1 2 3 to itself, it's going to of course have to send 1 3 2 to itself. And if that's the case, as well, phi of 1 3 2 1 squared is going to be equal to 1 3 2. Which in this case gets us that phi of 1 3 1 2 3 2 1 . 1, 3, 1, 2. One, 3, 1, 2. Phi of that is sent to 1, 2, 1, 3. All right. Which means that oh gosh, I'm not good with computations. The automorphisms of S3. Let's think. So we have that. We have that phi of 1, 3. Phi of 1, 2. Phi of 1, 3. Phi of 1, 2 is equal to 1, 2, 1, 3. Oh gosh, my head. I'm not made for this much computation. Compute out of S3 and in of S3 just, Okay, let's think. I mean, let's think about what determines an automorphism of S3. So first of all, an automorphism sends one of these between each other. And it sends one of these between each other. Or one of these three between each other. And the thing is, these three, oh yeah, let me think. So yeah, these three permutations are just built up from these elements, the transpositions. So the only thing that actually matters is where the transpositions are sent. Because as long as the transpositions are sent to one another, which they must by order, they'll naturally build up the rest of it, and they'll naturally actually uniquely determine the automorphisms. So we have the automorphism that sends 1, 2 to 1, 3. Oh, we can start actually, oh no, we can start using permutation notation to describe these permutations. So we have the permutation 1, 2 goes to 1, 3. Well, first of all, we also have to include the identity automorphism. We have the automorphism 1, 2. 1, 2. Wait, are you telling me that S3 is going to be isomorphic to its automorphism group? That's actually kind of wild. Which means, oh, if so, that's actually a really cool way to prove that the centralizer of S3 is actually nothing. It's 0. Oh, that is cool. That is I did not expect the result to be that wild. 1, 2 goes to 1, 3. 1, 2 goes to 2, 3. Alright, actually, no, before I jump the horse. So if, we have the identity permutation. We have 1, 2 goes to 1, 3. We have 1, 2 goes to 2, 3. We have 1, 3 goes to 2, 3. Alright, 1, 3 goes to 2. Oh, I should have noticed that when we could start using permutation notation that actually described itself. Oh my gosh. Then we have the permutation, which sends 1 to 2, 1, 2 to 2, 3, and then 2, 3 to 1, 3. And we have 1, 2 goes to 1, 3. Goes to 2, 3. Yeah, so this will be the automorphism group. And that means that also, I'm wondering, so how many transpositions are in Sn? So Sn contains 1, 2, so we have, so yeah, we have, oh man, oh that's cool. Actually now this makes me want to discover a more general fact. The automorphism group of S3 is in fact isomorphic to S3, which is kind of wild. Shh, that's kind of wild. I don't think it will be the case that it necessarily, actually it will be the case. I think every automorphism group of the permutation group is going to be another permutation group. But let's think about it. S sub 2 or S sub 1 contains one thing, but like that's weird, so we're not going to consider that. So S sub 2 contains 1 transposition. S sub 3 contains 3 transpositions. S sub 4 contains, we have 1, 2. For this we have 1, 2. I'll just not even worry about that. 1, 2, 1, 3. 2, 3. Then for S4, we have 1, 2, 1, 3, 2, 3. But then we have 1, 4, 2, 4, 3, 4. Oh, because we add n minus 1 transpositions. Oh, we add n minus 1. So this is 1, this is 1 plus 2. So the oh, this is bizarre. The automorphism group of S sub n is equal to S sub the sum from I equals 1 to n minus 1 of I. That's a bizarre result. Although it does kind of make sense that the automorphism group of a permutation group is going to yet again be the permutation group. Or is it going to be permutation group? So I equal, so yeah, for example, we have S2 is S1. S3 is, this is the only time where this sum equals your input, n. And then S4 is going to be S6. And the wild thing is that we can use the We can then also say by an inductive identity that this is going to be S of n minus 1 over 2. Which, that's a weird way to define that sum, but you can actually do that. That's wild. Okay. What the hell? So automorphism group of Sn is isomorphic to the automorphism group of the permutation group on n symbols is isomorphic to the permutation group on n times n minus 1 over 2 symbols. What? Oh, that's so cool. That's so cool. And double checking, just in case you're just tuning in and you want the proof of this, it's because every isomorphism of, actually, I should quick prove that. Every isomorphism of S sub n, actually, no, I don't even really need to prove it, because, yeah, I don't really even need to prove it, because the injectivity shows why it's a permutation, why it must be bijective, and we can just literally use the group theoretic, or group preserving property of automorphisms to determine that. So, dang, that's a cool result. I'm gonna quick bring that to the side and screenshot that later, because I'm proud. And the other, the inner group of S3 is actually going to be oh yeah, the inner automorphism group is itself wait, let me double check. Alright, compute, actually, yeah, let's just determine the inner automorphism group. So, for example, 1, 2, 1, 2, sigma, 1, 2. So 1, 2, sigma 1, 2 sends 1 to 2, 2 to something. Yeah, it's not necessarily trivial in this case. So phi sends the identity to identity. It sends 1, 2 to 1, 2. It sends 1, 3 to 1 maps to 2, 1 maps to 2, 2 maps to 1, 1 maps to 3. It maps 2, 3 to 1 maps to 2, 2 maps to 3, and then 3 maps to 2. And then from here we can either use these identities or we can do a direct computation for the 1, 2, 3 is mapped to 1, 3, 1, 2, 3 is mapped to 1 goes to 2, 2 goes to 3. Wait, no, I'm failing. Alright, 1 goes to 2, 2 goes to 3. So 1 goes to 3. Oh, wait, yeah. And then 3 would go to 2, and then 2 would go to 1. Yeah. 1, 2, 1, 3, 1, 3, 2, 3. And then, I actually don't even really need to compute this last one. We know 1, 3, 2 is mapped to 2, 3 by the fact that the inner automorphism is an automorphism. check. I mean, this doesn't feel right thinking about it. So 1, 2 is sent to 1, 2, right? 1, 2. It goes to 2, 1. Goes back to 1, 2. 1, 3. 1 goes to 2. 2 goes to... I think I joshed up. Give me a second to fix it. Because it sends order 2 elements to order 2 elements. So 1, 2 goes to 2, 2. 1, 2. 2, 3 is sent to... 1 goes to 2. 2 goes to 3. Then 3 is sent to 1, and 1 is sent to 2. 3 goes to 2. Then 2 would go to 1. And 1 would go to 2. No. Oh, what am I doing wrong? Okay. Oh, because 3 goes to 2. I was being dumb. Okay. Because 3 would go to 1. Oh no, 3 would go to 2, then 2 would go to 1. Then let's check this. 1, 3. We have that 1 is sent to 2, and then 2 is sent to 1. So 1 is stays with itself. Then we know that 2 is sent to 1. 1 is sent to 3. Yes, okay. So 1, 2 is sent to the permutation. 1, 2 is sent to the permutation. Gosh, I really need to calculate more because my basic calculation game is off. 1, 3, and 2, 3. We know the identity is sent to the identity. And we know that 2, 3 is sent to, let's think about it. So 2, 3 is, oh, under all these, oh, 2, 3 is mapped to itself. And then because it switches around things, it permutes the 2 that it's not. So 1, 3. 2, 2, 3, and then 1, 3 is mapped to, yeah, okay. 1, 3, 1, 2. And the other permutations are determined by compositions of these permutations. Oh, that's sick. Okay. Alright, find all homomorphisms phi of z to z. What is automorphism of z? Automorphism of z is phi from z to z. Well, it's going to be the set of all phi of, we proved previously, it's going to send phi of k to nk. And it's only going to be an isomorphism if n equals plus minus 1. So automorphism of z is isomorphic to the integers mod 2. It's one way of actually defining multiplication in this case, it looks like. Oh no. Yeah, this is actually the previous example we worked out explicitly, because kn is kn is congruent to 0 mod n, just by definition, because we're multiplying something by n. If is an isomorphism if and only k is a generator of Zn. Yeah, because first of all, it's determined by where it sends 1, and then we can do something cyclic from there. Show that every automorphism is used for Z. Yeah, this is just determined by the fact that every automorphism of Zn is of the form phi of k, where k is a generator. K as a generator is the same thing as saying that Un is in K. And then the isomorphism structure just simply comes from k times m is equal to phi of k times m. Yeah, this is a really good session. I quite enjoyed this, and I now understand isomorphism and group-related structure stuff way more than I did when I studied this a while ago. Like, during that, I was kind of like blanking out on a lot of it, and I was like, I mean, I get that it's important, but I don't get why. In this, we were able to define stuff. We had a bunch of identities. We proved that S sub n is equal to is isomorphic to S sub n times n minus 1 over 2, which was one of the most wild results of the entire rad. We showed precisely all homomorphisms between two cyclic groups, between cyclic groups of two orders, and showed what form they must take. Although we sadly didn't calculate them, which is something that I should have done, but I won't because I'm lazy now. It was a good day, and I think that should be it until next time with matrix groups and symmetry. This chapter right here, it scares me. So I'm gonna head off stream while I mentally prepare for that, because I might be streaming this chapter later tonight. Hint, hint, wink, wink, hint, hint. I'm scared. Please, someone be there to watch me struggle. Shh. Anyways. Thanks for tuning in. Have a nice day.